Okay, let's get started. I hope you all enjoyed lunch and are well rested for this afternoon session with Darren Vengroff. So this session will be about US Census data in Python. But before we start, I want to introduce you to Darren. And so Darren is Senior Vice President for Two Sigma. He works in New York, so he flew in over the weekend or last Friday and had some time to spend here in Seattle. So he's not fully jet-lagged. Yeah, and he has a PhD in computer science from Brown University and is a volunteering data scientist for Community Coalition on Race. So if you have questions regarding that, or you have questions regarding the workshop today, feel free to check in with him afterwards and ask those questions. But we'll pass it on now to Darren.
All right, thank you. Can everyone hear me? Yeah, okay. Thank you for the introduction, and thanks everyone for coming. This being a tutorial format, as you can see, I don't have slides. I'll actually be presenting from a notebook, or a couple of different notebooks. If you haven't had a chance yet, or hopefully some of you had, to go to the GitHub repo where these notebooks are housed, and there's a link there where you can actually run them live from a container at mybinder.org. If you'd like to follow along that way. No promises there. You know, if there are some network issues or sometimes my binder is a little on the slow side, I won't have time to stop and debug those. You'll have to just follow along on the main screen. But you know, if it does work for you and you want to change a few things here and there, you know, please do so. All right, so just a little background and history on what I'm going to be talking about today. So the origin story of the package I'm going to be talking about is probably a little different than some of the others you'll hear about today and the next couple days. So it started out at the Community Coalition on Race. So this is a 25-year-old organization in New Jersey that is dedicated to encouraging stable diversity and integration in the communities it serves. So, you know, diversity and integration are not the same thing. You can have a diverse town, but you know, if all the black people live on this side and all the white people live on that side, it's not integrated. So they've been doing this, like I said, for 25 years. Census data is a big part of what they use. And when they started, the way you got census data was you literally mail ordered it, right? You wrote a check, you sent it to the Census Bureau, and they shipped you a CD-ROM that had the data you wanted on it. So, been doing that for years. 2020 is about time to maybe try something a little more modern. That's when I got involved, and we started using the Census API through an existing Python package that was called Census Data. And then we built our own package on top of that called div-int-seg for diversity, integration, and segregation that could analyze this data and compute some of those metrics and give you an entire another talk about the various methodologies there. It's super interesting stuff. And that worked really well until 2022 when support for census data ended. Right? So now we had this interface we liked that would be written on top of it. We had the diversity, integration, and segregation code that we really liked on top of that. And the bottom had kind of fallen out from underneath. So we just bit the bullet and said, all right, let's just write the new bottom layer of that stack. And that's where census disk came from. So the open source or the package we've now open sourced, which I'm going to talk about today. So I've also used that elsewhere. So at Two Sigma, my day job when I'm not volunteering at CCR, we have a group called the Data Clinic that does pro bono data science work for a variety of nonprofits in different fields. We recently did a project with Housing Navigator of Massachusetts This is a nonprofit, and what they do is they've gathered a really solid proprietary data set on availability of affordable housing within their state. And then what we did is we helped them build kind of a census data side of that, bring them together and generate some interesting new insights. There's actually a blog post that didn't quite get published in time, but I'll post a link for it shortly after this. It should be out next week. And then more recently, I used the same code to build an interactive map of the entire United States. You can find it at the URL there. And you can zoom in and out and see exactly where the diverse and/or integrated areas are in the United States at all different zoom levels. And all the data retrieval from the census and analysis was all done with this package. And then fast forward to now, here we are at PyData Seattle. Thanks everyone for coming to hear about this. So just a quick outline of kind of the remainder of our 90 minutes. So in the first half, I'm going to jump right in. And this is intended to be hands-on, so I'm going to go straight to a hello world query, get some data, and then we'll really build up from there, look at getting different variables, different geographies, understanding how we can plot those on a map and manipulate them. And then towards the end of the first half of the presentation, I'll kind of go back to the beginning and say, well, how did we know these variables even exist? This is sometimes the hardest problem with census data. You've got over 1,000 different data sets. Some of them have tens of thousands of variables. So how do we actually discover the variables that we used in the example that I'm going to start with? So I'll talk about that. That'll get us a little over halfway through the 90 minutes. I'll give everyone a 5-minute break to kind of stand up and stretch your legs a bit. And then in the second half, we'll go kind of from front to back, starting with the metadata and discovery on a project where we'll start, just with a basic research question like, where are there children living in poverty in Newark, New Jersey? And we'll go all the way from where do we find the variables on that, how do we download them, how do we generate a map that actually shows these things in a way that we might present to a client or agency. And then finally, there'll be time at the end for discussion, Q&A. There's actually a third notebook that's a little bit more of a Mad Lib that can get you started on your own research question, where you can fill in sort of what you're looking for and follow basically the recipe that I did in the Newark example. All right, with that, so let's jump right into our first hello world query. So for every query we're ever going to make from the Census API, we're going to need to know 4 things, or we're going to need to specify 4 things. One is what's called the data set. So the census publishes lots of different data sets. Some of them have many variables, some of them have very few, some of them cover only certain ranges of time, some of them have been going on for a long time. We'll use one initially called the American Community Survey, or ACS. This is probably the most widely used census data set. It's very wide, it covers a lot of years. It's quite a detailed survey. I was actually thrilled recently. I got in the mail a flyer from the Census Bureau. I was actually selected to participate in the survey this year, which has never happened. So I guess, some years down the road, something I wrote in that survey might appear in this data set. But the next thing is the vintage. So we'll use the vintage 2020. So vintage is just when the data is from. And obviously, all the variables change over time, so we have to specify what point in time we're looking for. The third thing is, what variable do we actually want? In this example, I'll look for median household income. I'll just one variable. And then the geography, right? So these data sets cover a lot of different geographies. In this case, since we're in Seattle, I'll ask for Washington State, right? So my query is, according to the ACS data set, in the year 2020, what was the median household income? Now you'll see the variable here for median household income is B19013_001E. So I'm sure you're all very familiar with that, but in reality, every variable that they publish has some funky alphanumeric name like that. And like I said, we'll get to how we discovered that was median household income, but for now, just take my word for it. And then the geography, I'm going to call this API with this constant, which is the state of Washington, right? And so I run that, and what I get back is this data frame. It's an ordinary pandas data frame. I can do whatever I would do with data frames. And what does it actually contain, right? So it contains one row for each geography we asked for. We only asked for the state of Washington, so we only get one row. And it has two columns. The first column is state. It doesn't really tell us much here because we only asked for one state. And the value there, 5.3, that's something called a FIPS code. That's a code that the census uses to represent states and counties. So 53 is the FIPS code for the state of Washington. And then finally, the last value, 77,006. That's the data we actually wanted. The median household income in the state of Washington in 2020 was $77,006. Okay, so pretty simple query. Let's extend it a little bit. And what I'll do as I go through these examples is I'll leave typically a bunch of the arguments the same, and then I'll put a comment on whatever I've changed. And so here, in this case, what I'm saying is, well, I don't care just about Washington, I'd like all three states on the West Coast, right? So instead I passed a list of the constants for Washington, Oregon, and California. Not surprisingly, I got back 3 rows in the data frame, 1 for each state. And of course, 06 is California, which if you look at census data all the time, you would know, and probably none of you know or recognize. 5.3 is Washington, which has not quite as high a median household income as California, and then 41 is Oregon, which is lower. So those aren't super friendly. So there's something I add pretty much to every query I ever do, which is this other variable whose name is just name, right? So I say, median household income and whatever else I want to query, but also give me this variable name. And that name is just the name of the geography, right? So now I get that column back, I have something, probably a lot more useful. Certainly if I'm then gonna put that on a chart and want to use those as labels or something, right? So I just added that name to the list of variables that I wanted. So next thing I can do is I can say, well, I might not want just those 3 states, I might want all of them. And I can type out all 50 constants, but I don't want to do that. So instead, I can just pass a wildcard, right? I can say state equals star, and now that's going to get me a data frame that, again, has all the states in it. Actually, if you notice, the data frame has 52 rows, not 50 as I would expect. And the reason is because it also includes Washington, D.C. and Puerto Rico. So these aren't states, but the Census Bureau considers them to be state-like enough that typically when you query for state data, in most data sets, you'll get DC and Puerto Rico data as well. So this is a completely ordinary pandas data frame I got back, right? So we can do completely ordinary pandas data frame type of things with it, right? So for example, if I want to say, well, what are the 10 states with the largest median income? I just use the method nlargest on that data frame that I just downloaded from the census, give it the variable I want, and here are the top 10 in descending order. You'll notice actually number 1 is Washington, D.C., a non-state, right? And then Maryland, New Jersey, etc. Down the line. Or if I wanted to get the bottom 10, same thing, but it's n smallest method on the data frame. And in this case, actually, it turns out both ends of the spectrum are the two or the district and the territory that aren't states in terms of median income anyway. But again, they're grouped in there. Okay, great. So a lot of times when I'm dealing with data that has to do with states or counties or whatever other geography, I'd like to visualize that on a map, right? I'd like to be able to present that to, whatever my final audience is in terms of the map. And in order to do that, I have to be able to somehow get, what is the geometry of each state or county or whatever. And I can do that very simply just by adding this one argument, this one optional argument, with geometry is true, right? And if I set that to true, what happens? Well, instead of getting back an ordinary data frame, I get something called a geodata frame, which some of you may be familiar with. It looks and smells pretty much exactly like an ordinary data frame, except it has this extra special column called geometry, right? And if I look at geometry, for every state in the data frame, I have either a polygon, like in the case of Pennsylvania, that has all the lat longs of line segments that draw the outline of the state, right? Or in the case of California, it's a multi-polygon because California has the big mainland piece and then a few, Catalina and a few other islands are their own polygons. Typically, coastal states, I'll see a multi-polygon. Interior states usually are just a single polygon. But now that I have those polygons, and I also have the median household income in each of those states, I can plot those results on a map very easily. And we created this convenience method, plot US, that makes it easy to do that. I could just plot the geodata frame itself. The reason we have this API is because it produces maps like this. You'll notice that it does things like it relocates Alaska and Hawaii down here, where Mexico would normally be, to save space and not leave a bunch of empty Pacific Ocean in between. It relocates Puerto Rico as well. It also uses a map projection where, you can see the 49th parallel here on the Canadian border is curved as it often is. And it just kind of looks a little nicer for presentation than just a straight line across. It's a view that most of us are accustomed to seeing. And then every state is filled in with a color based on its median household income, right? So I just said, use this variable, this data frame full of states, and then I added a couple of keyword args like add a legend and how big I wanted the figure to be. It uses matplotlib under the covers, and so you can add any keyword args you want that matplotlib would understand and pass them through, and they will affect the plot. And so actually, if we do that, in this example, I just added a few more. I chose a different color map, changed some colors and line widths, and then I set the min and max values of the household income. So, this picture is, depending on your view, maybe a little more pleasing than the earlier ones, right? And I can see exactly which states have, relatively higher or lower median household incomes. All right, so we've been talking about states up to now, right? We loaded this data just at the state level. Census data comes in all different kinds of geographies, not just state, right? So now I'm going to look at a few of those different geographies. So I'm going to make the same query, although actually I'm only going to query for name because I'm more interested in just showing what some of these geographies look like at this point. And I ask for all the states, and I plot them, and sure enough, I get a very familiar map of the United States. But if I wanted to zoom in a little bit, let's say I don't want to know just say the median household income for Washington State. I want to know it on a county by county basis within Washington State, right? So what I can do is I can specify my geometry not by just saying state equals Washington or state equals star to get all the states, but saying state is Washington and county is star. So this is saying get the data at the county level for every county in Washington State, right? And if I plot those, here's Washington State, here's King County where we are right now, and the various other counties. And I can keep zooming in with the same basic approach, right? I can zoom into King County. So first I need to know what the FIPS code of King County is so that I can query for it. And so again, this is an ordinary data frame. So I just look for what row in that data frame has a name that starts with King, right? And there's only one. Its name is King County, Washington. And there we go. I know its FIPS code is 33. So what I'll do then is I'll zoom into that county by specifying not star, but that specific county. And then I'm going to ask for something called a census tract. So every county is divided up into what the Census Bureau calls census tracts. These are areas where typically between 1 and 5,000 people live, right? So if I do that, again, I just say state of Washington, I say the specific county I want, and then I say all tracts, so all census tracts. And it looks like this, right? So over here on the western side of the county, downtown Seattle, Capitol Hill, and so on, these census tracts are very dense, right? The population is dense in those urban areas. Whereas if I go out to the eastern side of the county, the census tracts are much bigger geographically. So the reason for that, of course, is they all have somewhere in the sort of 1 to 5,000 people range. And so whenever you look at a map like this, you can always tell where the urban areas are because the census tracts are much smaller, where the rural areas are where they're much larger. Okay, the next level and the finest level of that's available in the ACS data, the American Community Survey data that we've been looking at, is something called a block group. Some of the data sets actually go down to individual city blocks, and we'll see that later. But the ACS goes down to a block group, which is kind of a collection of blocks, somewhere between 500 and 1,000 people, somewhere in that range. And same thing if we plot them on the map, right? They're super, super dense in the urban areas, a little less dense in the suburbs over here on this side of Lake Washington. And then in the rural areas, they're still massive. There just aren't a lot of people living over there, right? So we've looked at the geographies and kind of what they look like, but we really want to get census data, right? We want to do things like our query for median household income. So we can do that here. All I did is I added back in the median household income variable. So I have name and median household income. Same thing, I want all the block groups in all the tracts in King County. And then this final additional argument I added, there are some cases where the census API will return special values, and they typically look like minus 66666, like 9 sixes, minus 777, and so on. They're numeric, but they're basically specifying different reasons why there's no data for that particular geography. Sometimes it's like, it's an industrial area, no one actually lives there. Other times it's too few people live there, and for privacy reasons, they don't want to expose certain variables. There are a number of reasons, but what I'm going to do here is I'm going to say, okay, for now I don't care so much about the reason. I just want to say, if you see any of those special variables, set it to a not a number in the pandas data frame, and then in my work and the various tools I use, we're used to seeing not a numbers and dealing with them. So we'll do that, and then what we'll do is we will plot kind of a background color of purple, and then plot at the block group level our median household income, right? So now we have the whole county, right, super dense over here. The highest median household income is sort of along Lake Washington here, and then a little further out in kind of the exurbs. Some of the southern part of the county, quite a bit lower median household income, and somewhere in the middle in the rural areas. So, in just one quick query and call to the plot API, I've got a map of King County with a lot of potentially useful information on it in terms of what the median household income is. All right, so we dug down from state to county to census tract to block group. That's what the census tract refers to as or what the Census Bureau refers to as an on-spine geometry. What that means is every level of the hierarchy completely tiles and fills the level outside it, right? So there's no place in a state that's not in a county. There's no place in a county that's not in a census tract. But they also publish tons of different what's called off-spine geographies, right? So these are geographies that don't necessarily fill the whole plane, but are useful and interesting in a variety of ways, right? And so we're going to make our sort of first step into metadata by trying to ask, well, what are some of these other geographies that are available, right? And this is a little visualization of kind of what they look like. The on-spine is in the middle, and then there are these various other things, places, urban growth areas, urban areas, that each has their own kind of definition of what they are. They're actually more than are even shown in this picture, and we'll see that now by querying. We can just say, okay, what geographies are available for the data set, right? We say, what's available for the ACS 5 that we've been using in the vintage 2020. And we get all these results, right? And every single one of these little lists is a set of valid parameters, keyword args that we could pass when we want to download data, right? So before, already we used state and county. We used state and county and tract. We didn't do county subdivision, but there are, basically using a combination of constants and wildcards, I can query, data at any of these different levels. Some of them nest inside states, some of them don't. Some of them are very sparse. And you can see there's a whole lot of them, right? So I'm going to start with one, one of the early rows in there specified state and place. So a place in census terminology is typically in an incorporated area, right? So it's a city or a town, or in some states like New Jersey, there are townships and villages, which are slightly different, but they all are called places, right? And they're off spine, so they don't necessarily fill up the whole state. There are gaps in between, right? So if I query for median household income and I say state of Washington, all places, then what I get back is a data frame, that has all the places, and I have all their names, right? The first one is Aberdeen, right? So any Nirvana fans in the audience, that's where they got their start, and plenty of other different places in Washington. And so now if I plot those, what I can do is, first thing I'm going to do is get the outline of all of Washington, so I can plot that in like a beige background color. And then I say, okay, on top of that, I want to plot the median household income of all these places, right? And sort of style and format that a little bit. And so now I have this, right? You can see there are a lot of places over here in Western Washington, different cities, towns, suburbs, and so on. Out in Eastern Washington, they're a lot more sparse. It doesn't mean no one lives in these gaps in between, but it means there aren't sort of formal incorporated places there. And depending on how I want to present this data, instead of drawing the background map of Washington State myself, what I could do is add this with background equals true argument. I wasn't using that before because it wasn't really relevant. I was on spine and I would have covered everything up anyway. But if I do specify that, then it downloads some tiles from OpenStreetMaps, uses those as the background, and produces a map where you can see the roads and sort of where the different towns are along these roads and rivers and so on. All right, so let's look at one more kind of geography. So places were within states. There's another commonly used kind of geography that some people call a CBSA, or core-based statistical area. It's made up of either what's called a micropolitan area, which is a area with a population between 10 and 50,000, or a metropolitan area, which is an area with 50,000 or more people. But you'll notice in the query we did above, the metadata query, it doesn't nest inside state. So CBSAs can cross state boundaries, right? They're not bound by that nesting. And in fact, they very often do, right? So here I'll query, the median household income, and then this other variable, B03-002_001E, which is total population. So I'm gonna get the name, median household income, and total population of every CBSA in the country. And then because I don't want to plot them all, I just want to plot the 100 largest, I'll say, okay, let me take the 100 largest, filtered out of that data frame I got back. Plot those on a map of the US, and here's what I get, right? So now I see the 100 largest metropolitan areas. Here's Seattle. Here's the Portland metro area, which actually crosses the border into Washington State, some of the suburbs like Vancouver. Places like in Missouri, both Kansas City and St. Louis metro areas cross state lines and go into other states, right? And I can also very quickly look at this and say, oh, the one with the highest median income is the DC CBSA, which includes parts of Maryland and Virginia, right? And San Francisco and Oakland are pretty high up there next as well. All right, so we've queried, the geographies for one particular data set. Not all data sets actually support all geographies. And so we can look at other data sets. So there's another commonly used data set called Public Law 94-171. This is, unlike the ACS, it's only published once every 10 years, and its primary purpose is for redistricting congressional districts, right? So it has fewer variables. It has population and some ethnicity and race variables, but it has them over a very large number of areas, right? So if we compare over the years the geographies, and all I'm really doing here is counting for the ACS how many different geography paths were available each year, usually about 80. For some reason in 2017 and 2018, they dropped 2 of them, and then in 2019 or 2020, they either replaced them or brought them back. But then you can see, like in the public law data set, it's only published once every 10 years, and back in 2000, it had very few geographies available, only 28. But nowadays, it actually has more than are available in the ACS. In fact, it actually has some that go down to the block level that I was talking about before, right? So we've talked about how to discover the geometries that are available for a particular data set, but we haven't talked about how to discover data sets and, more importantly, the variables that they contain. So that's what we're going to do next, which will eventually get us back to the median household income variable that we've been using all along. So how do we discover data sets? Well, there's a simple API for that. We just ask for all data sets. And what we get back, like basically all our APIs, is a data frame. And this data frame, you can see it's got over 1,300 rows, and it's telling us about all these different data sets that exist in different vintages over the years, right? So, there's one for county business patterns, so we can dig into that. There's probably, all kinds of economic variables in that one. There's some, post-secondary employment outcomes, right? So data about how people are employed post-secondary education, right? And there are a lot more in between, right? So I could scroll through all of these, or because it's a data frame, I can just, kind of grep through it essentially. I just say, well, I'm looking for data sets whose title contains, American Community Survey 5 here, right? And that's probably not the first query I did. The first one was probably ACS, or American Community Survey, and I got more results than this. But 2 or 3 attempts in, I got down to this, nice little set of data sets. And you can see each one has a year, and then, ACS, ACS5, that's how I knew what to pass to the data API, right? I got it from this metadata API. And there are sub data sets that, not a lot of people use as much as the main ACS, but that have additional information derived from the ACS, right? So now that I've found the data set I want, I have to find the variables that I want. And because there are so many variables in a lot of data sets, they tend to be organized into groups. So I can query for a given data set in a given year, what are all the groups of variables that are available? And that's what I did here for the ACS5 in 2020. And you can see, each one has this alphanumeric name, and then it has a description, right? So sex by age is the first one, but then there's, public health insurance data is kind of the last one. There's all kinds of other social, demographic, and economic data in the 1,100 rows that are in between here. So 1,100 different groups. I'm looking for median household income, which I'll come back to in a minute. But let's just look at one other data set, right? The ACS has 1,100 different groups. If we go back to that public law data set, it had more geometries and very narrow geometries, but it actually only has 6 groups of variables, right? It's done once every 10 years for a very specific purpose, and it only has these small number of groups of variables about population, race, and ethnicity. Okay, so back to finding our median household income. So we can search through the groups and look for median household income in their description. You'll see, there's actually a bunch, there's 20 or so here, different groups of variables, all that talk about median household income in one way or another, right? So there's this one at the top that's just, median household income in the last 12 months in 2020 dollars. That's probably where we want to go, right? That's the most basic and not tied up with anything else data set. But there are other data sets. So for example, there's this one, median household income in the past 12 months by tenure. So tenure in the census parlance means, are people homeowners or are they renters, right? So we could look in that data set and find out, what are the differences in median household income between owners and renters, for example. But this one looks like the one I probably want to use, so I can take the next step down the hierarchy and say, for that group, what variables does it contain, right? So the data set, the vintage, the group, and it turns out this one only contains one variable. Most groups contain more than one variable. This one only contains one, and it's our old friend, B190013 or 013 underscore 001E, right? And we can read the label. It's median household income. So that's how what I did in the last few cells. That's how, before I started, I actually found out what that variable was that we used in our Hello World queries. I was able to, in just a few queries, drill down through the data set, the group, and the variable to find what I want. So I mentioned, most groups have more than one variable. Here's one that has 3, right? So this is that other one that's median household income by tenure, and you can see it has a first variable, median household income total. So that's everybody, right? And then it has a variable for owner-occupied households. So this is just the people who own their homes, what's their median income. And then it has another one for renters, right? So that total, that should have the same values as that other variable I just had, but the other two break it down into 2 subgroups, right? So These variable groups, you can kind of see it if you parse it out with these bang bang and some other special characters they use, but there's an implied tree here, right? And so we can look at that tree in a more friendly format just by asking, group tree. So what are the variables in the group organized as a tree, right? And you see here, again, the total variable household income for everyone, and it's divided into two pieces that are the leaves of the tree, the owner occupied and the renter occupied. Okay, so some trees are much deeper than that. Here's an example from the public law, decennial public law data set that we were talking about before. So this tree has at its very top a variable, which is total population, everyone who lives in that state or county or block or whatever. And then it has one leaf, which is Hispanic or Latino. So everyone who identifies ethnically as Hispanic or Latino is counted in that variable, which is also a leaf of the tree. But it has a sibling called not Hispanic or Latino, so that's everyone else. And for those people, this particular data set goes deeper. On the Hispanic or Latino side, it stops, but it goes deeper elsewhere, and then divides people up into people who reported belonging to one racial group and what they reported, were they white, black, Asian, whatever they reported being. And then there's another sibling of that for people who reported they were of two or more races. And the tree goes down, and as you can see, it gets very, very deep, and has a great deal of detail in terms of exactly what it covers. Okay, so sometimes we want just the leaves, particularly when we're dealing with demographic data and looking at things like diversity and integration. We just want the leaves. We don't want the intermediate nodes where we're summing stuff up in the middle, or we're going to end up having problems double counting people. So we could, kind of walk that tree and come up with a list, or we can just ask the API, what are the leaves, right? And then it tells us. Remember, in that first group we looked at, there were only two leaves for the renters and the owners. In this bigger one, there are a lot more leaves, and then there were those various internal nodes as well. So if I want to query all the variables in a group, or maybe all the leaves, there are simple APIs for that, right? In fact, we go back to the same API we were using before, and I just specify that I want the name variable, but then I say, okay, get me also all the variables that are in this group, right? So I didn't have to list them out. It will go and do that metadata query, figure out what they are, and get the data for me. And so it did that, and sure enough, I've got the name, and then I've got the three variables, right? So in California, where my overall median household income was 78,000 and change, among homeowners, it's over 100,000, right? And we'd expect homeowners to typically have higher median income. Among renters, it's much lower. And we see that same pattern in the other states that we queried. So sometimes we want just the leaves, as I mentioned. So instead of saying group equals, I can just say leaves of group equals. And in this case, with this small tree, it just left out the root. It left out the one for everybody and just has the one column for homeowners and the other column for renters. If we look at the leaves of a much larger tree, so this is that tree on race and ethnicity that went really deep and had tons of leaves. That group is called P2, and I query that group for the 3 states, and you see I get my 3 rows, but I get a very, very wide data set in this case, right? So, and what it tells me, California has 15 million people who identify as being Hispanic or Latino. It has 13.7 million who don't but identify as being white, and so on and so forth, all the way across the table. All right, so we are halfway through our 90 minutes, 45 minutes in, I think just about on the dot. Pretty happy with that. So at this point, I wanted to give you a chance to take a 5-minute break, get up, stretch your legs. We'll reconvene in 5 minutes, and we'll put everything that we've just been talking about together into one case study where we'll look at, how can we identify areas where there's significant childhood poverty in Newark, New Jersey. So I'll see you all back here at 20 after. Thank you. Oh, and there's also a bunch of resources you may want to take a look at during the break as well, if you're interested. There's an optional API.
City of LA, just like before. Yeah.
There's, in fact, in the documentation, there's a little to show you how to register for an API key. Or what I do is I file and this will just grab it.
No one thinks it's that secret. Yeah, if you so all the
they're not
so the hierarchy.
they serve
If I have my secret, it's like
Well, I've been doing this crazy.
Thank you.
Yeah, we should have me.
It hasn't it's going to be, I thought it would be published sometime this conference. The nonprofit partner didn't do the final approval yet, so we couldn't publish it, but it should be next week.
So. Yeah, sure, happy to.
And no, I wasn't sure whether this was opposed to, hey, you know, I've got a full research area. She ended up replying to me about have a great time with PyData, you know, protect people. But I'm really worried that it's too solid.
I mean, I don't find that it's good for real-time
All right, why don't we get started again? Hope everyone enjoyed their brief break from 90-minute presentation. So as promised, I'm going to now show, sort of how we put this all together, going actually in the correct order this time. From, we have a research question to we actually have an output that has an interesting answer to that research question. So the particular scenario that we're going to look at is we have this, maybe we're working with the city or a nonprofit or other government agency, but for one reason or another, we want to know, where in Newark, New Jersey, are there concentrations of children living in poverty? Because we want to develop some services, presumably, that are going to assist them in getting out of poverty. So, I'll skip over the basic imports, but first question we have to ask is, what data do we want? What are the groups and the variables? Kind of the thing I was doing towards the end of the first half of this presentation. And so I'm going to start with the ACS data set just because it's so broad and so wide and has so many things in it. I have a pretty good hunch that it has things about poverty in it. So I'm going to look at that, and I'm going to look in this case, vintage 2021, and I'm going to ignore that warning. And then what I'm going to do is, just like I did before, I'm going to say, okay, let me get all the groups of variables that are available in that vintage from the ACS, right? And then I'm going to say, okay, well, let me look for the ones that somewhere in the description, contain the word poverty and contain the word age, right? Because I'm interested specifically in children. A lot of data sets are grouped by age groups, so that's probably going to help me find it, right? And well, it turns out, like I keep saying, there are a lot of groups and a lot of variables, especially in the ACS, but also even in a lot of the others. Some of them are very, very specific, right? Like poverty status in the past 12 months of grandparents living with their own grandchildren under 18 years by responsibility for their own grandchildren. So, there's going to be different groups of whether they are the primary caregiver or not within that data set. So, like I said, you don't get this many data sets or this many variables and groups without having some very, very narrow ones, right? So then there's another one here, poverty status in the past 12 months by sex and age. That's kind of promising, right? That's gonna have poverty status, at least grouped by age, and although it's grouped by gender as well. So if we were studying specifically, girls living in poverty, that would probably be a great data set. If we have to, we can use it, right? We can add up, we can sum them up. But it turns out, let me actually find it here. Yeah, here's the one. Here's one that is actually, oh no, that's the wrong one. Here we go, perfect. All right, B17020, this highlighted row, right? Poverty status in the past 12 months by age. So this is going to tell us how many people in a particular area are in poverty by different age groups, right? So let's go with that one. So we'll make a constant for that group. And then I say, okay, let me look at the tree of variables that's actually in that group so I can understand how it's structured. And, you know, like most trees, at the top it's got total. So that's just going to be the total population in a given area, right? And then on one branch of the tree, I'm going to have people whose income in the past 12 months was below the poverty level, right? So this will be everyone of all ages. And on the other side of the tree, I have people above the poverty level, right? So those two nodes will add up to the sum that was at the root. And then going further down, I can see they're actually divided up by age group, right? There's not formally a variable for, you know, children or under 18, but there are three separate variables that I can very easily add up, right, to get the total that I want, even though, you know, they could have, for example, put another level of the tree for children and adults, and then further divided it, and that would have had the sum I wanted. They didn't do that, so I'm just going to add up the three that I want, right? So I just, you know, rather than try to do this programmatically, I just kind of visually look at the tree and say, okay, these are the three variables that I want, right? These are people living below the poverty line that are under 18 years old. Okay, so now I come to the geography side, right? I've got the variables I want. I need to know the geography. So as we saw before, most cities and towns are usually designated places by the Census Bureau, right? So I'm going to query this data. I'm going to query the data set, the vintage, and the just the name variable for all places in New Jersey, right? Because I don't really care about all places in New Jersey, but this is how I'm going to find Newark. And then I'm just going to say, okay, which one has a name that starts with Newark? Sometimes there's more than one, depending on the state. But here, no, there's Newark City in New Jersey, and its place is 51000, right? So I'll make another constant for that. So basically, this is just kind of my general workflow from research question through the notebook, step by step, to kind of figure out, you know, what constants, what variables, what geographies, and so on I'm going to need before I finally get down to being able to do my actual data query. Okay, so then I'm going to download the name and then those three variables that I want that add up to the number I want for the Newark in the state of New Jersey. And I'll go ahead and get the geometry too, just to make sure I'm on the right track, right? So here it is. I've got the three variables. This is how many children live in Newark that are in poverty in each of those three age groups. So quite a few, right? Almost, 8,000 or 9,000 in each of those. So quite a lot. And then I often like to do kind of a quick visual reference, right? So I downloaded the geography along with that. And so I'll plot that map with the background overlay so that I can just sort of visually see, yeah, I didn't make some weird mistake and got some tiny town on the other end of the state, by mistake, right? Here's, Newark Airport, the Port of Newark, Ironbound, and, all downtown over here. But, it looks like Newark, right? It's got this funny little piece that sticks off it that actually dates from the 1920s when Newark tried to annex a bunch of local towns, and a lot of them resisted, but the 3 or 4 here kind of created this little isthmus that is part of Newark to this day. Anyway, okay, so what we actually want, though, is narrower data, right? We want tract level data because we want to go down to narrower regions within Newark in order to look at where those children living in poverty actually live within the city of Newark. Now, the problem we're going to run into, of course, is that places are off-spine geometries, whereas these are on-spine geometries, right? So these don't necessarily exist within places, right? There may be some census tracts that are a little bit inside the place, but mostly outside it, or vice versa. So what I'm going to do is I'm going to get all of the census tracts in the county, Essex County, that I happen to know that Newark is in. And you know, I could have queried all the counties and looked up Essex, and I would have found it's 013, kind of like I found King County in Washington, but I happen to know that, so I just put it in. And then I visually inspect by plotting a map, you know, where are all these census tracts in the county, and then where is Newark, right? So Newark is this blue outline, and then this is all of Essex County. And just like we saw before, you know, the urban areas are more dense, you know, the more rural areas out in this part of the county are less dense, and there's, you know, some suburbs in here, you know, that's like, I guess, Bloomfield, Montclair, places like that are still pretty dense. But now what we want to do is we want to get just those census tracts that are inside Newark, right? We don't care, at least for the moment, what's going on out here. And so we want to filter, and so what we can do, the geo data frame that we've been using, that extension of the data frame that has geometry, has a variety of geometric operations it supports. So we can, you know, intersect and union and whatever. And the problem is, if I do a spatial join with, so I'm doing that right here, I'm taking all the tracts in Essex that have the data I want in them, and doing a spatial join with Newark, which I had that one row in the data table I downloaded, and then I want to plot that and just make sure I got the right answer, and it looks like this, right? So what went wrong here? And this is a super, super common problem when you're dealing with geographies, right? So some of these census tracts, like this one, you know, the actual boundary of them, you know, maybe whoever was making that map plotted that boundary like down the middle of the street or down the left side of the street. And whoever was plotting the boundary of Newark plotted it down the right side of the street. So there's a tiny intersection there, and that's why this one showed up, right? Whereas here, you know, this is the Passaic River running along here, and you know, the towns that are on the other side of the river, probably whoever drew their boundaries and drew those census tracts, you know, they use the width of the river and they don't intersect, right? So how do I deal with this? Well, you know, of course what I could do is say, well, let me find the area of intersection of all of these and find the ones where it's, you know, big and not small and so on. And that works, and in fact, that's what we're gonna do. But it gets really hairy because these are all in latitude and longitude. And depending on how you project it onto a plane, the areas are different. And you really shouldn't do that when they're lat long. You shouldn't compute the area in terms of lat long. You should use some kind of projection where you're in a coordinate space where you're measuring meters in X and Y, and then compute the area, and then compute the intersection of the area, and figure out, you know, which ones really belong. And so that's what we do, but we wrapped it all up in this API, right? Spatial join mostly contains. And so what this does all that projection I was just talking about, computes the areas, and then by default says, okay, you join with Newark if more than 80% of your area is within that boundary. Now you can change that threshold with an optional argument. You can make it 90 or 95 or whatever other number you want it to be. But the default almost always works, and if we plot the results, here's what we get, right? We've got the census tracts that look like, you know, by and large, in fact, in this case, none of them even poke out enough that they look like they're outside at all. Sometimes they do, depending on what state and what places, and then you have to kind of decide what you do with it. But we got a really good result here, right? And again, we've got, you know, small census tracts here in the densely populated parts of town. This is like, you know, Newark Airport and the Port of Newark, right? This vast area, but, you know, pretty much no one lives there, and so that's why it's so large. But this visual inspection step I find is really important, just to, you know, make sure we know what we're talking about before we try and do anything with the data. Okay, so now we can actually do our analysis, right? And our analysis in this case is actually really simple, right? We just have to add up those three variables. But our data at this point is in an ordinary pandas data frame. We could use, you know, arbitrary machine learning models from, you know, sklearn or XGBoost or like whatever we want, as long as we put the results back in the data frame along with the geometry, you know, then we have something super interesting, right? So here, you know, I'll just add up the three, and then, you know, right here, just make a new column and sum those three variables, right? Super simple. Normally there would be, you know, that would be kind of the meaty part of the notebook where we did our modeling and analysis. But then I plot them, and here's what I get, right? So now I can see exactly where children are living in poverty in large numbers in Newark, including this, you know, part that sticks out a little bit here. And then, you know, I can look at the top 10, so I can say, okay, which of the census tracts have the most, or I can then do that visually, you know, plot those top 10 census tracts by the most children living in poverty and see where they are in Newark, overlaid on a map where I can see what's going on. So, you know, we're pretty close, if not all the way there, to something that, you know, we could present to that agency that we're working with, and to, you know, to people who aren't data scientists and aren't, you know, fluent in this sort of thing. But, you know, basically anyone can look at this map and say, okay, I see what's going on here, I see what's going on there. You know, super interesting cases like this little tip out here that's actually in Newark. It turns out this area around it here, that's like South Orange and Maplewood, which are much more affluent suburbs. And there's a very popular park, you can kind of see it right there, you know, just across outside Newark. And I actually talked to a local historian at one point who told me that, you know, as late as the 1990s, kind of right along the main street there, 24/7, there would be a South Orange police cruiser parked there to make sure that no kids from Newark came and used that park. You know, as late as the 1990s. And you can see poverty persists among children in that area to this day. Like, yes?
So alternatively, you could do rate of poverty, right? Because right now you're just summing the number of kids, not dividing by the population of the kids. To get population of kids, you probably have to access another variable, right? Because you don't have it right now, right?
That's correct. And that absolutely. And so, you know, that's an example. You could do it as a percent of the total number of kids or of the overall population. Yes, absolutely. You know, this is sort of just the bare bones showing you the type of analysis that you can do. But again, once you have that data downloaded, yeah, the sky's the limit in terms of how you analyze it. So with that, you know, as I said, we kind of are there, and in you know, literally what, 20 minutes, we're able to go from a you know, a research question to finding where the data lives within the census's, you know, vast collection of variables and groups, get the geographies, filter that, you know, clean it up, plot it, and really be ready to go. So with that, I think I will jump to, let's see, you know, more of a open-ended discussion at this point in our remaining time. So first, you know, thanks everyone for attending. There's also some other, like as I mentioned, there's another notebook you can take a look at. It's in the GitHub repo. That's kind of a plug and play repository for doing projects like this. Take a look at that. We've got, how long, what, 20 minutes?
Yeah.
20 minutes for questions. There are a couple of mics. If you can speak into the mic, that would be great. Happy to talk about any of this. I'm also around for the next couple days as well, so feel free to grab me at lunch or one of the breaks. I'll be around and happy to chat. Yes?
Thank you. Is there any support for distance from certain points? As a example, like how many people within a radius of like 10 miles live from a certain area, or an airport, or whatever.
Right. So great question. So you can do that. You can't do that directly in the API because the underlying data model looks different than that. But what you can do is, and what I've done in the past for queries like that, is you go down to the lowest level of granularity that your data set has. Like for a query like that, if I could get a data set that went down to the block level, I'd do it. Otherwise, I'd go to the block group. And then I'd say, okay, from this given point, I'd probably, depending on how big the radius is, but I'd probably say, get the counties for the state. See how many of them, using the spatial join functionality of the geodata frames, I'd say, how many of these counties have at least part of them within that radius at that point? Then as I did here, I'd say, well, which of the blocks are part of those? I wouldn't really care about the ones that missed a little on the outside, and then I'd just join those with based on distance to get the circle and add them up. And I'd get a little noise around the edges, but that's how we typically approach that kind of question. Yes?
I saw when you were getting the data from the poverty by age, it said estimate.
Yeah.
Can you explain what that means?
Sure. Yeah. So the American Community Survey that we got that data from is, as its name implies, a survey. So unlike the decennial census that happens every 10 years, where their goal is to talk to or get a form filled out by literally every single person in the country, the community survey is a survey. And so that almost all the variables are qualified with that estimate because it is, this is our best estimate of the number. We didn't talk to everybody. There are other variables you can get as part of those data sets that tell you things about margin of error. And you can look at like the margin of error at different geography levels and so on. To the extent that that really matters to you, you can sort of do these very bounded kind of analysis where you study the error bars and even how they propagate through your analysis. But that's why they call it estimate, because they are, but they also provide additional data on what they believe the accuracy of those estimates to be based on the sample sizes.
Just a follow-up question.
Oh, sorry.
So just to follow up, does that estimate, so do they define what poverty is? What is the value?
Yes, they do.
That's in the census data somewhere that says, hey, for this year, the poverty line is at this value.
It's published by a different agency, but the census, yes, their numbers refer to that official federal line.
I had to actually look that up last week. Poverty is defined as 3 times the basket of food you need to buy for the week. So if you were earning less than 3 times how much you pay for food, you were in poverty. I think it's the Department of Commerce decides how much food you need to eat for the week and how much it's going to cost. So when people are doing like actual poverty estimates, they usually go with twice that. They do twice the federal poverty level. Where I come from in Baltimore County, for a family of 4, it's like 50,000. Good luck feeding a family of 4 and keeping them in a house for 50,000 a year. It's quite tight. The question I had, the reason I stuck my hand up, you showed this way of grepping through all the different tables that you have. Is there like a Google for census fields? Like, can I just type in African American income 20 percentile, right, and it'll show me which table and which field in that table I need to look at? Because that's always the thing that slows me down when I'm using the census.
Yeah, so there are, these data sets and tables and groups that I all went down through, there are web pages that are essentially tables rendered from this. I'm sure you've probably seen them. Or maybe...
Yeah, no.
Oh, well...
I have searched in vain.
They do exist in some obscure corner of the Census Department's website. The best way I've found to do it with that is somehow find that page and then literally just Control F and search through it. That's why we do it this way.
Yeah, I understand. Thank you.
From your experience, are there any pitfalls or common things you've run across, say the difference between cities and townships that might throw people off, or because states can define things differently, are there problems comparing apples to apples sometimes?
Yeah, that's a great question. There are a few. The state of Massachusetts is a particularly strange one for whatever reason, in that the way they have, and probably because they did this however many hundreds of years ago, they did it probably before the United States even existed, but they've divided up the whole state into, I forget what they call them, but the Census Bureau calls them county subdivisions. But in and around Boston, they really pretty much are the towns. And in the other part of the state, they're not really. And so that's one that Massachusetts definitely trips people up in that way. And if you're not from Massachusetts or don't regularly use Massachusetts data, we found this out the hard way working with Housing Navigator of Massachusetts. That's why I know this. But yeah, that's the one really strange one that I know about, and where you have to be very careful.
I was just going to say, something that I have found is that sometimes counties will change names. I think there's Lakota County in South Dakota, and so the FIPS code changes for that county as well. So if you didn't notice that, you may have a blank spot in your map if you're specifying the FIPS code you're looking for.
Yes, that's absolutely right, and there are other versions of that same problem. So as soon as you're ever trying to do a study that goes across from year to year to year, you sometimes run into problems like that. Even in the definition of what a census tract is, right? Because as I mentioned, typically between 1 and 5,000 people. Well, over time, people move around a lot, and some of these census tracts, their population explodes. So what does the Census Bureau do? They cut that census tract into 2 or 3, and each of which has a number that didn't exist before, and the number that existed before no longer exists. Same thing as the counties you were talking about. And so you have to, if you want to do a study involving, what happened over the course of the last 10 years, you absolutely have to, from year to year, do that same kind of geometric analysis where I found what was part of Newark to even well, wait a minute, this census tract disappeared, but what was it replaced with? And then you have to remember, well, okay, then I'm going to have to sum those 3 up because they represent what last year was one census tract.
Just adding on to one more thing that, to answer your question, that might you find weird in census data. Virginia has some, I think they call them independent cities or towns, where in a normal sense, ostensibly, it would be what would be like the county seat of a county, but if you look at the shapefile on the map, it's a completely separate entity from the rest of the county. And sometimes they even have the same names. It's just one of those weird things I ran into one time. Yeah, it's in Virginia. Yeah, so some of the cities are just, they have the same name as the county that completely, geometrically surrounds them. But it's a totally separate entity, totally separate governmental body that governs it.
Question about cadastral information. Do you have any land ownership data set in the whole API?
Land ownership, no, just because that tends to be, like the deeds are typically at the county level, and it's, I have done some work where I needed to do that, and I, in one case, was super lucky that the county had an API, and in a couple other cases, it's basically you scrape their website. That's the only way to do it that I've found. Yes.
I might have skipped this at the beginning, but when do you start using GIS or GIS versus this type of tool? When would you say you would start using GIS? In the same way, when you can use GIS for some reason and this tool is more helpful?
Sure. So you're talking about GIS systems like Esri and stuff like that, right? So yeah, I mean, there's a whole industry that's built all those tools, and they're very much built for, importing all kinds of data, not just census data, but lots of other things, and, doing a lot of the geometric and spatial stuff, typically in an interactive GUI kind of application, right? And there are, people that spend their entire day in front of these and build beautiful maps of all kinds of things. I think the sort of, when would you want to go that route and when would you want to go this route? I think the advantage here is kind of the piece that I didn't really show, or I kind of glossed over right at the very end, is the analysis piece, right? You get in this world, you get a whole bunch of data from the census, and now you want to use sklearn, you want to use, XGBoost, you want to model it, StatsMod, whatever the entire ecosystem of Python, machine learning, statistical analysis, that kind of thing. This data, once you've gotten it this way, is ready to go into that world. I mean, I guess the other difference is, those high-end GIS systems, they can do some incredible things. They are not inexpensive. Yes, back corner.
Hi, does the all datasets capacity include datasets from other organizations like the USDA that also have datasets by census tract, like a food atlas, research atlas?
Sure. So the census, through their API, does, I don't know about that specific data set, but there are definitely, from the Department of Commerce in particular, there are data sets that are derived from census data, the analysis is done by the Commerce Department, and then they're published back through this same API.
Thank you.
This question is slightly off topic, so apologies.
That's okay.
When you were showing Washington State, right,
Yeah.
you have a whole bunch of really, really tiny census tracts in the cities and a whole bunch of really, really big census tracts in rural areas. And so anything that you plot at that state level, whatever's going on in the rural areas is going to dominate the image visually,
yes.
right? You have much more experience in this than probably most of the people here. How do you deal with that? How do you stop the story of the rural areas dominating the story of the urban areas when you're making the plots?
Fantastic question. So in the same way that, you know, that I projected the United States so it like looked nice as if you're looking down from space and whatever. Except somehow Alaska was down here. There are projections that are, you know, where the area is based not on area of land, but on some other variable. And they're typically done with a sort of Monte Carlo or simulated annealing type of approach, where what you do is you say, oh, you know, you start with the map as it exists, and then you say, oh, this area, you know, the area that I plotted relative to the population is either way too big or way too small. And so if it's way too big, let me shrink it a little bit. And it'll sort of pull its neighbors in with it. And also some I'll expand, right? And you do that iteratively until you get something relatively stable. And depending, like sometimes it looks totally crazy and you can't tell what's going on. But other times, like I've seen it done at the state level, and you get a map of the United States that's very recognizable as a map of the United States, but like the middle is squished down to nothing and the coasts are really big, right? So, I mean, this tool doesn't do any of that, but that's how I've seen it done. All right, anything else? Or should I let you go enjoy the break before the next session?
Yes. Thank you very much, Darren.
Okay, thank you everyone.